So how do we actually configure target 3 in a way that lets it retain its configuration while we're changing the configuration of target 2? So here's the solution. So step 1, control channel equals 1, program channel equals this. And this is the cell we configure in step 1. Step 2, control channel equals 0, program channel equals, and in this case we want to take a 1, put it into the C input so that target 3 will be configured, but we're going to do something slightly different. We're going to take the data coming from the west and the data coming from the east, and we're going to OR them. And that's going to be the data we send out to the east. Step 3, so this is cell configured in step 2. Step 3, we change our initial target cell into a pure data router without the C output being asserted. So in step 3, we configure this cell to take data from the west and pass it to the east. But notice that in step 3, we've already started to configure target 3. And so this is being configured in step 3. In step 4, we take our desired truth table configuration and we send it through the initial target cell. This truth table, the bits get passed from west to east in this cell, and in this cell they get passed from west. They get ORed with what's coming out of target 3. Well, if target 3 starts off with all zeros in its truth table, we OR these incoming bits with a 0. We're just taking bits from the west and passing them to the east. And so again, we are simply configuring target 3 with its desired truth table bits, and at the end of step 4 it will be in its final configuration. Now we need to undo what we've done in cell 2, and so in step 5 we have to begin to unwind all of this. So we set CC to 1 and we set PC to the same thing it was in step 1. Take data, pass it from west to east, put a 1 into the control input. So this is step 5. And it's worth noting that in step 5, target 3 is again configured with its desired configuration, because in step 5 we've put this cell into C mode, which means its C output is 0, which means this cell is in D mode, which means it's executing its program, which looks like this. So cell 2 is asserting a 1 to its control east output. Target 3 is still in C mode. We're putting zeros into the western input of this, because since this cell is in C mode, its eastern D output is 0. So we're putting zeros in over here, but this cell in configuration mode is pumping out the old bits of its truth table, and those are getting ORed with a 0 and sent back in. So it's non-destructively reading and rewriting its current configuration. So in step 5, target 3 is being reconfigured again, but with the same program that it had at the end of step 4. So step 5, this is modified. And then in step 6, we could do whatever we wanted. We might just decide we're going to clear out these 2 cells. So in step 6, we set the control channel to 0. This old target cell goes back into D mode, which means it can assert its C output, and now cell 2 is in C mode. Since 2 is in C mode, its C output is deasserted, and target 3 returns to D mode, so this will not be configured anymore. In step 6, we're going to configure this, and that will be its final configuration. I'm just loading zeros in there for fun, but we might, put in some other sort of useful cell. Whatever we want this cell to ultimately be, that's what we put out on the program channel in step 6. And then in step 7, control channel equals 1, PC equals whatever we want to put into there. And in step 7, this cell is configured, it enters its final state, and when we're done, return the control channel to 0, at least briefly, and we are finished. And we've successfully configured this cell and this cell and this cell after initially having access only to this as the target cell. So that's an example of how we configure things more than one spot removed from the target cell. There's one wrinkle in here though. Remember, in step 3, target 3 is being configured, and it's being configured via the one output from this cell and the fact that it's ORing bits that are coming out of the truth table with bits coming in from the west, which are 0. But this means if there was some initial non-zero truth table in target 3, we can never get rid of those ones, because the nature of an OR is you can set a bit but you cannot clear a bit. So in order for this whole process to work, we need to make sure that target 3 is initially empty. So we actually need some initial steps in between steps 1 and 2. Before we build this OR circuit and let it go live, we need to pre-clear target 3. So I would add some additional steps over here. For example, step 1.1. So first we configure this cell to configure this one. 1.1, we're going to set control channel equal to 0, program channel equals something like this. So we configure this to be a program that simply puts target 3 into C mode but sends zeros into its D inputs. So we're going to configure this in step 1.1, and then in 1.2 we're going to reconfigure this exactly the same as it already is. And this is a peculiar thing to be doing at first glance. Because this is already how this cell is configured, why do we want to write the same configuration back into it? Well, we don't. What we want to do is put this cell into C mode, because when we put this into C mode, this cell will go into D mode, and the way we've written this in D mode, when this cell is operating, when it's interpreting its truth table, it will assert 1 to its C output, which will place this into C mode. So the point of step 1.2 is not so much to change this cell's truth table, it's to allow this cell to become what we call live, to assert its C outputs. Because in doing that, target 3 will be zeroed out. So in step 1.2, target 3 is configured, and we're put in parentheses to indicate that what's happening in step 1.2 is it's actually being zeroed out. So now it's zeroed out. Now we go back to step 2, where we go ahead and return the control channel to 0. So this cell becomes live, and we route this configuration into here. So in step 2, this gets configured, and at the end of step 2, step 3, this will start being reconfigured, but we'll have 0 bits coming out of here and 0 bits coming in because this is in C mode, and so we'll be loading more zeros into target 3's truth table, and it will be a non-detrimental operation. And we actually won't write any 1s into target 3 until we get down to step 4, when we're actually putting our desired bits in. So that's the entire sequence of operations, and it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 operations. This is one reason we don't build wires longer than 2 or 3 spots away from the head cells. Using this kind of approach, this is another reason why we want the extendable 2-channel wire. So being able to do this one spot removed, this will also let us configure this remote corner down here in doing our wire building sequence for the corner, because it's the same thing. We're using this cell to configure this one. We're going to need to turn this into an OR configuration block before we can actually load this remote corner's truth table. So next and final video in the sequence will show the programming steps for building a corner.